The human brain is amazing and complex. It grants us the ability to think outside the box. However, because of this immense processing power, many psychologists and neuroscientists who study sensory systems and perception assume that we do not directly perceive and act in the world. Rather, our perceptions, thoughts, and actions depend on internal transformations or computations that occur in our minds. It's because of these processes that some of us see this dress as black and blue, while others see the dress as white and gold. In actuality, this dress is only one color, black and blue. But after the picture of this dress was posted online, it led to an intense back and forth debate on social media about what the true color was. So how can the same exact object be seen so differently? Our minds make transformations and compensate based on external cues. It's because of this transformation that people see the dress as different colors. People who believe the ambient light in the room was dark when the picture was taken perceive the dress as white and gold, while those who believe the ambient light was brighter perceive the dress as blue and black. Let's take a look at this video from ASAP Science for an in-depth explanation with animations.
Alright, so the world has seemingly become utterly divided on this dress. What colors do you see? On the one hand, we have team black and blue, on the other, team white and gold. We asked on Twitter and got hundreds of responses for both white and gold and black and blue. For what it's worth, we both saw black and blue and thought this was a massive prank at first. So how can it be possible for people to see it so differently? It's a phenomenon known as color constancy. Take this cube, for example. The middle square on the top appears to be a shade of brown, while the one on the side looks much more orange. But in actuality, they're both the exact same color. We promise we haven't cheated here or done any trick photography. Instead, our brain looks at the context, sees a shadow, and instantly thinks, oh, shadows make objects appear darker. And so the brain compensates and interprets the square as lighter than it appears, until the shadow is taken away. Back to the dress, and we have a similar situation, except here the context is very arbitrary. We're so close up to the dress that we don't really know its surroundings, and the brain has to make assumptions. People who picture the dress as white have brains which may be interpreting the dress in a blue lit room, for example, as in it's near a window with a bright blue sky. It makes perfect sense then that the white dress would be tinted blue and that the gold color wouldn't really change. On the other hand, the brains of people who see it as black and blue may be interpreting the dress in an artificially lit setting like somewhere with yellow lights. As a result, the brain sees the gold as just a reflection off of the black and believes that the blue has been unaffected. Chances are that this image just happens to be perfectly ambiguous to our brain, meaning it all comes down to individual perception and even how and where you view the image. From a factual standpoint, the dress is blue. In fact, here are some other pictures of it. But this is a beautiful example of how our brains have evolved to interpret the world around us without us even realizing.
So from this, it's clear that what we see with our eyes may not be exactly what we see with our minds. To understand this, we first need to understand the difference between sensation and perception. After we have done so, we can then describe the world based on principles that apply to all senses. We'll then apply these concepts to different senses, particularly vision and taste. Getting to our first objective, what is the difference between sensation and perception? For either to take place, there first has to be some form of external stimuli in the world to be detected. Sensation comes first. It's the initial process by which sense organs respond to these external stimuli. Each sensory organ is specialized to capture a particular form of energy. Our eyes detect visual external stimuli in the form of light waves. Our ears receive it in the form of auditory waves. Our noses from chemicals that lead to smells, our tongues from chemicals that lead to taste, and skin from pressure and touch. So how do these organs take these external stimuli and transmit the responses to our brains? We'll first focus particularly on vision, because all of us can see it, and it is the sense we rely on the most. For this to ever take place, we first need to have a visual stimulus. Our common sense tells us that our vision works like a camera, that our experience of the world is simply delivered to us via our senses. But this would be naive realism. We know this can't be the case because of phenomena like the blue dress. Because like the dress, we have what are known as illusions, misinterpretations of sensory information. Illusions make some of us see the dress as black and blue, and others see it as white and gold. And we have these spinning wheels. If you focus on just one wheel, you'll see that they aren't actually spinning, but our minds think that they are. What does this actually tell us? Illusion tells us that our experience of the world is actively constructed. Our minds are constantly transforming information. That in addition to sensation, there is perception. And perception is the additional processing of sensory signals by the brain that makes us see the crazy things that may not actually be reality. So how can illusions, or how we perceive stimuli, help us understand how we sense stimuli? This leads into our second learning objective, properties of sensory receptors, and how these properties can influence perception. The first property of sensory receptors starts with energy in the world, those external stimuli that are present. Receptors need to be there to convert that energy into neural activity. This is a process known as transduction. You can think about transduction similar to radio waves. A signal is transmitted as waves, but in order to actually hear the sound, there has to be an antenna on a radio or a television to pick up the waves. Sensation works in the same way. There has to be a receptor that transduces the energy. For the visual system, light energy is converted to chemical energy in the photoreceptors of the retina, and this chemical energy is in turn converted to action potentials. If there are no photoreceptors to pick up the energy, then no signal is detected. This principle can be demonstrated using an optical illusion. Take a look at the large dot. It's just a large dot moving back and forth. Nothing really special about it. Now close your left eye and look at the small dot with your right eye. Depending on the size of your screen, the large dot may seem to disappear, but it's not really disappearing. It's just our brains telling us that it has disappeared because of how the stimulus is perceived. So why do we perceive it this way? Why does our brain seem to lose the signal? Again, the photoreceptors are like the radio antenna for detecting light waves. They sit in the back of the eye on an area known as the retina, which you can see highlighted here in yellow. So when we see something, like this pencil, the light coming from the pencil goes to the back of each eye, where photoreceptors are located to detect the stimulus. Let's now zoom in to just a tiny portion of the retina. If we look at the zoomed in portion of the retina, you'll see that it consists of layers of cells. At the very back of the retina is a layer of cells that are colored purple and green. These purple and green cells, if we zoom in even closer, are the photoreceptors. So light enters the eye, goes all the way to the back of the eye, where it is then picked up by these photoreceptors. These are separated into two classes. In green, we have cones due to their cone-like appearance. Cones work well for perceiving color and give you high acuity, but they are not as sensitive to dim light. On the other hand, we have rods, shown here in purple, taking on this rod-like appearance. They work well in low light conditions, but they're also colorblind. So these are the two types of antenna in our eye. So why, in the case of our large dot, does the signal sometimes get sent to our brain, and why does the signal sometimes get blocked from getting into our brains? Well, you'll see that a feature we previously identified, the optic nerve, innervates the eye to send signals to our brains. From there, the information passes along the optic tract to some familiar players. First, the thalamus, which then relays the information back to the occipital lobe and the visual cortical areas. So the optic nerve is essential for allowing the information to get into the brain. But the optic nerve running through here also creates a problem. Because we know that photoreceptors on the retina are essential as the antenna to detect signals. However, when the optic nerve comes into the eye, It creates a gap in the retina at a spot known as the optic disc. This gap means that there is no antenna present and no detection of signals is possible. So the optic disc produces what we call the blind spot, because the area of the retina that can detect light, or the receptive field, is located on the retina outside the optic nerve innervating the eye. Here's a zoomed in view again showing the photoreceptors at the back of the eye in the retina, and then the optic nerve which is innervating the retina, creating a gap where there are no receptors and the signal can't be detected. So why does the large dot disappear? As the dot passes through our retina, it passes through the blind spot, blocking the information from getting into our eyes. How else can illusions help us understand how the brain senses and perceives visual information? This dot is just black and white. We haven't even gotten into the complexities of color. How are they detected? And how does this relate to our perception? Recall that cones are essential to detect colors. And we are aware of 3 different cones: those that respond to blue, those that respond to green, and those that respond to red. Because there are 3 different cone types, the interaction can influence our perception. For example, let's stare at this flag for about 15 seconds. It looks a little funky now with all the wacky colors. But once we shift to a blank screen, we see the real colors of the flag appear. So how can this be explained? The opponent process theory suggests that we perceive colors in terms of 3 pairs of opponent cells: red or green, blue or yellow, and black or white. The idea is that when we see something green, like the bars of the flag we viewed previously, visual areas of the thalamus responding to green spots are excited, while cells in the thalamus responding to red spots are inhibited. When the inhibition is finally removed on the red neuron, it responds with a burst of activity, setting a signal that red is actually being perceived. Let's take a look at another example. Stare at this red dot in the center of the screen for about 15 seconds. If we take a look at the next screen, we see a bright after image of yellow sunflowers in the blue sky. One final example is the lilac illusion. So you may immediately see a green dot moving in a circle, but in actuality, this is all red. This is because, you may recall, that the opponent process theory states that red would inhibit green responding neurons. So every time a red dot disappears, it produces the perception of a green dot. The disappearing in sequential order makes it seem like there is a motion taking place, and that motion is transferred to the green. Now that we've identified the first principle of sensory receptors, we can now move on to the second, the principle that receptor density determines sensitivity. Let's return to how the eye works. We now know that light must hit the retina in order to be detected by photoreceptors that are there. In particular, the eye focuses light onto what is known as the fovea, the center of the retina. This is important because the fovea has the greatest density of photoreceptors. You'll see from this graph that on the y-axis we have receptor density, and on the x-axis is the location on the retina. At the very center, 0 degrees here, is the fovea, and the highest point on the graph here along the y-axis. But there's a problem here. You'll notice that this peak is colored in green, the same color as our cones, which are represented by these green dots. This is because the fovea only contains cones, and no rods are present. So what does this mean? Well, we know that the fovea is essential for fine discrimination and contains only cones. As light decreases, we lose our ability to use our cones for fine discrimination because they're not sensitive to low light conditions. We begin to rely on our rods in the periphery of the retina, where acuity is not as great. Most of us have probably had this experience where it starts to get dark and we're playing a sport like soccer or basketball. All of a sudden, the ball smacks you right in the head. Why do we lose the ball? Well, we know that we use rods more in the dark. The problem with this is that when we want to focus on an object best, we need to focus it onto the fovea, where, unfortunately, only cones are present and are not active in low light conditions. Hence, losing the ball and having it hit us right in the face. How else can differences in rods and cones explain changes in perception? Let's take a look at this example. If you close your right eye and look at the circle, and then start your thumb at the X, let's take a look at what happens. If I move to the next screen, it may appear blank to you. If we move to the next slide, the red H was there the entire time, but it was blocked. Why? Because it was located in the periphery. And remember, in the periphery of the eye, only rods are located, which are not sensitive to colors. The cones, which are sensitive to colors, start to disappear as you move further and further away from the fovea. Cones are also not distributed evenly by color in the retina. So different parts of the retina are more sensitive to different colors. We'll test this sensitivity during Lab 8, where we'll map out the photoreceptors. In Lab 9, we'll test out this principle that receptor density determines sensitivity by performing a 2-point discrimination test of touch. You will most likely find that receptor density is highest where fine discrimination is most important, like your lips and your fingertips. The final sensory lab we'll complete during class is the taste lab, where we'll examine supertasters and multimodal integration. Many of the concepts we've already discussed can be applied to this lab. We'll also examine with the taste lab how senses interact to alter perception. In addition to describing how our sensory systems detect chemicals for taste, we'll finish with this concept of sensory interactions. The chemical senses are taste and smell. Smell and taste are known as the chemical senses because they detect chemicals in the environment. Interactions between the chemical senses of taste and smell enhance our perceptions of the foods we eat. For smell, these chemicals come in the form of odorants that bind to olfactory receptors. Olfactory receptors are located in a part of the nose known as the olfactory epithelium. As you can see, the cilia of these olfactory receptors actually reach out into the nose, so they can be damaged easily. As Medina mentions, the only thing separating these cells from odors are boogers, so they're susceptible to damage. Luckily, they can grow back. After the chemical is detected in the nose, these neurons synapse at the olfactory bulb, which we previously identified, so the signal can then be passed along to the brain. What makes the olfactory pathway unique is that unlike all the other senses that need to pass through that relay center of the thalamus, it has a direct connection to the cortex, at the piriform cortex in particular, and to the amygdala. These direct connections from olfaction make smells emotionally salient. We've discussed how the amygdala and hippocampus have strong connections with one another, so it makes sense that smells would evoke such powerful emotions and memories. Perhaps the smell of cookies take you back to grandma's house, or the smell of a laundry detergent. These are all different chemicals our noses first detect, and then relay to emotionally charged areas of the brain. Outside of our nose, chemicals can also be detected by our tongues. There is a common misconception that chemicals relating to particular tastes, like sweet and sour, are specific to discrete parts of the tongue. A tongue phrenology, you might say. While it is true that our tongues have specific receptors for chemicals associated with these tastes, the receptors are actually distributed across the tongue. In taste, the receptors are the taste buds. Sweet receptors are sensitive to calorie-rich foods. Bitter taste receptors are sensitive to vegetable and a wide variety of toxic substances, helping us avoid them. Salt receptors are related to chemicals necessary for water balance. They are simply ion channels that allow sodium to enter. So when sodium dissociates from chloride and table salt, it directly activates the neurons through depolarization. Sour receptors are sensitive to acidity, particularly in fruits. The hydrogen ions from acids activate these receptors. And then we have umami receptors, which are sensitive to protein, creating the savory sensation. Another common misconception, though, regarding taste is that the bumps on the tongue are the taste buds themselves. In actuality, the bumps on the tongue are known as papillae, and the taste buds are actually buried deep inside the bumps along these trenches here. We can now apply the first principle of sensory receptors to taste. We know that receptors transduce energy. In this case, the energy comes from chemicals. The receptors in the taste buds respond to chemical substance that comes from a stimulus like the lemon, where the sour is then detected deep within the papillae trenches where the taste buds and taste receptors are actually located. Within the taste buds, there are receptors that can be responsive to a variety of tastes. So it's not true that one particular taste is confined to one part of the tongue. Instead, what is true is that these receptors are not evenly distributed. There is a gradient of concentration of receptors for each taste that is distributed across the entire tongue. So higher concentrations of sour on the side of the tongue and lower concentration towards the center. Bitter receptors are highest near the back of the tongue, but still present just at lower concentrations at the tip. So why would this influence our perception of taste? Well, we know that the second principle of sensory receptors is that receptor density determines sensitivity. So the higher concentration of receptors, the higher degree of sensitivity you will have to a particular taste. In people, the density and distribution of taste buds can vary due to variables such as age and genetics, making some of us more sensitive than others. We'll attempt to measure the variability with the final component of our taste lab. But what if we could alter the types of chemicals that our taste buds could detect? With the last part of the taste lab, we'll do this by getting to try a protein known as miraculin and a product called miracle berry. Miraculin binds to sweet receptors on the tongue. Once acid from a sour food is introduced, the miraculin protein changes shape in such a way that it turns on the sweet receptors it is bound to, causing an ultra-sweet sensation without affecting other flavors. We'll try out a variety of foods in an attempt to have their acids activate the sweet receptors on our tongues. But we don't need chemicals to alter our perception of taste. Our minds can do this on their own. Our senses are constantly interacting and blending to influence our perception. Think about several foods. We have a perception of how they will taste simply by looking at them. Even a mental representation of them can make us hungry. When we look at this green apple, it's almost as if we can taste it. A bit of sour and crisp. And the orange, its name itself is related to its colored appearance. So vision and taste do work together. Some companies attempt to capitalize on this with varying degrees of success. They use artificial colors to make their foods more appealing. They use slogans like "Taste the Rainbow." We have these particular representations of flavor based on appearance in our minds. It's why products like green ketchup and Pepsi Clear are often not as popular, even though their active flavor ingredients are identical. In the lab, we'll put our perception of taste to the test, and we'll be examining the relationship between these two senses firsthand. We'll choose from flavors of Starburst with sensory manipulations to see what we perceive. So sight, taste, and smell can all work together to influence our perception with multimodal integration, but they are not alone. Vision and sound also work together to influence our perception. For example, we have the McGurk effect. This is an effect that demonstrates how we experience cross-modal sensation, in this case visual and auditory. We read about this from Medina, and he demonstrates it here.
Watch this experiment. It's called the McGurk effect. ba, 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 ba.
What do you think he's saying? If you think he's saying da, 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 you are in the grand majority. But now, close your eyes and listen instead of watching.
Ba, 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 ba.
The voice is saying ba, ba, ba. Now, let's replay it without the sound. Yes, it's true. His lips are saying ga, ga, ga. So how is it that when the lips are saying ga, 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 and the sound says ba, 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 that our brains read da, da, da? The McGurk effect. It's an example of an auditory illusion. It's a great way to show that the accurate perception of information can involve the participation of more than one sensory system, in this case, vision with sound. We call it multimodal perception. The McGurk effect. It's a terrific example of the fact that the senses did not evolve in isolation from each other, but actually work together to help us perceive our world. When multiple senses are stimulated simultaneously, the brain begins to experience an information-rich learning experience and laps it up like ice cream. It encodes more information per unit time, and it remembers that information better too.
Taste and touch also interact. You probably noticed that when people eat spicy foods, they say that it's hot. This is because capsaicin, the chemical in peppers that make food taste spicy, bind to the same receptors that are activated by heat, producing similar perception. So by now, it is probably clear that what we think we see with our eyes or taste with our tongues may not be exactly what we see and taste with our minds. Sensory systems can interact, and this can clearly differ on an individual basis. When we get to our memory lecture next, we'll see a particular example of how perception can change from individual to individual based off of how our minds are wired and cross the senses, a phenomenon known as synesthesia. This is when the stimulation of one sense produces a reaction in others. Sometimes people will see different numbers as different colors. The 5s are in green and the 2s are in red. David Eagleman explains quite a few and other examples of this phenomenon.
One of the things I study in my lab is called synesthesia, and it represents a blending of the senses. So we've all heard the word anesthesia, which means no feeling. Synesthesia means joined feeling. So somebody with synesthesia, they might hear music and it causes them to see colors physically. Or they might hear something and it puts a taste in their mouth. Physically, they're experiencing that. Or they might eat something and it puts a feeling on their fingertips. The most common forms of synesthesia have to do with overlearned sequences like letters or numbers or weekdays or months triggering a color experience. So somebody might look at the number 6 and that's red to that synesthete, or they look at the letter J and that's purple. And it's an internal experience, it's automatic, it's involuntary, and it's unconscious. And to a synesthete, it's just self-evidently true that J is purple. And it used to be thought, this was very rare, the original estimates were 1 in 20,000, but we now know it's quite common. It's probably up to 4% of the population has some form of synesthesia. There are many different forms, essentially any cross-blending of the senses that you can think of. My colleagues and I have found a case somewhere. So we now know it's very common, and the reason it's so interesting to me is because it's a very good inroad into understanding how different brains can perceive reality differently. So you're sitting here, your neighbor's sitting here, and you're both looking at the same thing, and yet you're seeing the world very differently. And it turns out synesthesia is heritable, so my lab is pulling the genes for it right now. And the reason that's so interesting is because it's what I'm calling perceptual genomics, which is to say, how do little genetic changes change the way we perceive reality? And of course, most synesthetes historically have lived their whole lives, and they may even die without ever suspecting that they're seeing reality differently than someone else, because we all accept the reality presented to us. So synesthesia is a really direct way to look at how individual changes can lead to different beliefs about reality.
It was previously thought that people with synesthesia were extreme cases. But when you think about it, this may just be on a spectrum, just like we see with many psychological traits. Another more common form of synesthesia that has been recently identified is hearing motion. Here is a representation. Each movement of the block has a particular sound associated with it. Only 4% of the population are believed to experience synesthesia, but a recent report suggests that this specific form of the condition may be much more common. When participants were asked to remember locations of flashing lights, 1 in 5 participants said they could actually hear the motion. They were asked to identify whether patterns were the same or different, and those who reported synesthesia tended to be better at identifying identical patterns correctly. So this contributes to the evidence that multimodal processing can increase learning, just as Medina suggests. Something to think about as you progress through your studies and classes. How can you or your teachers take advantage of these principles to enhance learning and memory? We'll see directly how memory can be enhanced in our final lecture. For now, I'll let the Gorillaz get the final word with their poignant lyrics regarding perception.
God, y'all can see me now cause you don't see with your eye. You perceive with your mind, that's the end line. So I'ma stick around with Russ and be a mentor. Bust a few rhymes so motherfuckers remember what the thought is. I brought all this so you can survive when law is lawless. Feeling sensations that you thought was dead. No squealing, remember that it's all in your